everyone. Myself, Dr. Ranjith Kumar Gatla, working as an Associate Professor in the Department of Electrical and Electronic Engineering. So, welcome back to the course Electrical Circuits. So, in today's class, we are going to practice some numerical problems based on the star to delta or delta to star conversion as well as the mesh analysis. So, we have already discussed these concepts in earlier classes. Now, we are going to see when we are going to apply the star to delta connection or delta to star conversion, and as well as of course, because when we were discussing about the loop analysis or the mesh analysis, that time we were discussing about only the loops which are having only the two loops. Now, if more than two loops, so how we can apply this mesh analysis to evaluate the response of across any element. So here, this is the circuit. So for this circuit here, calculate the equivalent resistance between the terminals X and Y for the circuit shown in below. So, which means, as we know, we can easily identify whether the two resistors are in series or parallel. Okay. So here, for this circuit, we have to find the equivalent resistance between these two terminals X and Y. So, first let me start here. What are the two resistors are connected in series, or what are the two resistors which are connected in parallel? So here, if you see these 3 ohms and 3 ohms, these 3 ohms and 3 ohms are connected in series, because as I told you, so here how to identify the series? If the two resistors having only one common node, this is the one common node, and the common node should not share with or should not connect with any other element. So of course here the 3 ohms and 3 ohms are having only one common node, and this common node is not connected to any other element. So, and let me see, is there any other possibilities? Of course, these 6 and 6, of course having only one common node, but this common node is connected to 4 ohms resistor. So similarly here, as you can see, these 4 ohms and 5 ohms, these two are having only one common node, and that common node is not sharing with any other element. So here, these two are in series. So here, these series combination can be replaced as 3 plus 3, which is equal to 6 ohms resistor. Similarly here, these two also we can replace with the equivalent resistance, which is 4 plus 5, which is equal to 9 ohms. Right? So now let me draw here the equivalent circuit after replacing these 3 and 3 ohms combination with the equivalent resistance. So 3 and this is 6 again. So this is again 6 and this is again 8 and this is 4. This is 9 and again this is 9. So again here 5 plus 9, again this combination is 9. So here we should not disturb the terminals X and Y, because we have to find the equivalent resistance between these two terminals X and Y. So of course here we are replacing this 3 ohms with an equivalent resistance of 6 ohms, and again here 6 ohms is there, and again here 6 ohms is there. So here 8 ohms, and this is 4 ohms, and this is 9 ohms, and again here it is 9 ohms is there, and these two combination is we are replacing with again 4 plus 5 is 9 ohms. Right? So now let us see, what are the other two combinations that are series or parallel. Of course, first let me see with these two, 6 and 6. Of course, these two are having only one common node, but the common node is connected to the terminal which we are going to find. So we should not disturb this terminal. Okay, so we cannot take this. Then next, these 6 and 6. Okay, of course here 6 and 6 are having only one common node, but that common node is sharing with this 4 ohms resistor. So we cannot define this is series or parallel. Then similarly, the 6 and 8, again this is having one common node and the common node is connected to 6 ohms. So we cannot define whether the 6 and 8 are series or parallel. And again here 8 and 9 also one common node, and this common node is connected to this 9 ohms. So again, so which means here we are not going to, or we cannot identify, so whether the combination, whether 2 or more combinations of the resistors are connected in series or parallel. So in this case, then how we can reduce this network to find the equivalent resistance between the X and Y terminal. So now we are going for the star to delta or delta to star connection, right? So here So here, because let us take these three resistors, the 6 ohms and the 6 ohms resistor. Okay, so this is we can see this is in terms of a delta connection. Okay, so this delta connection can be replaced into star connection. So here, because here this is the three nodes. Okay, in between three nodes we should just you connect one star connection, right? And again here, with these 9 and 9 and 9, again this is a delta connection in between these three nodes, of course, because this is the same node. Okay, so let us consider here one node. So again we can just convert this one into, this delta is also into star network. Okay, then how we can convert this delta into star network, right? So here, suppose if you want to find this resistor, okay, let us consider here it is R1, R2 and R3, right? So here R1 equal to the two resistors which are connected to this particular node, okay, which are 6 ohms and 6 ohms. So 6 into 6 by the total resistance, okay, 6 and 6 and 6. So 6 plus 6, which is equal to 2 ohms resistor. Then similarly, if you want to find R2, of course here all the resistors values are 6, so that's why it is very easy to find. Again, what are the two resistors which are connected to R2? The 6 ohms and the 6 ohms. Again 6 into 6 by 6 plus 6, which is equal to again 2 ohms. Similarly, R3 is equal to also 2 ohms, right? Now we are going to find here, let us consider again here, this is R1 dash, R2 dash and R3 dash. So here also R1 dash is equal to the resistors which are connected to that particular nodes are 9 into 9 by the total resistance is 9 plus 9 plus 9. Okay, so now which is equal to 3 ohms. Similarly, R2 dash is equal to also 3 ohms, because here all the resistors having the same value, and similarly R3 dash is equal to also 3 ohms. Okay, so now just eliminate these resistors, okay, with or just replace this delta connection with the star connection, and the values of the star connected resistance are R1, R2, R3 in this case, okay, and in this case R1 dash, R2 dash and R3 dash, right? So now let us draw the circuit, okay, which is having the star connected networks, right? Okay, of course, before we are having this, because let us consider this node, we should not disturb the nodes. Here 8 ohms is there, and here the star connection 1 and another star connection and another resistor which is connected to star, right? So here for this we are having the X, right? And here of course one more resistor is there in here, the 4 ohms resistor, okay, and here also we are converting star, okay, so this is 3 ohms, 3 ohms, okay, again here the Y terminal is there, okay, and here again one more resistor like this, okay. So which means here we are just converting these delta into star, and after that we are replacing. Then what are these resistors here? Of course 2 ohms, 2 ohms and 2 ohms, and here we got 3 ohms, 3 ohms and 3 ohms, right? So which means here we are eliminating all these, I mean this, okay, and this one, okay, and we are converting these delta into star in these two cases. What are the two remaining resistance? Only 4 ohms and 8 ohms, right? So that's why here you can see this is 8 ohms and this is the 4 ohms. Okay, now we are going to simplify this circuit again. So how we are going to simplify this circuit again here? Okay, of course here as you can see these 2 ohms and 8 ohms and again these 3 ohms are connected in series. This 2, which means here 2 plus 8 plus 3, and here again this 2 ohms 2 plus, and again this 4 ohms 4 plus, again these 3 ohms are in series. So we can replace this one with the 13, replace with this 13 ohms resistor, and this is 9 ohms resistor. So now the circuit is, because other again here these 2 ohms is there and these 3 ohms is there. So let us draw the 2 ohms which is connected to the terminal X. Okay, and here one is in between these two terminals, one is 13 ohms resistor, and here one is 4 ohms, sorry, the 9 ohms resistor, and again here 3 ohms resistor is there which is connected to the terminal Y. So here it is 2 ohms resistor, and here it is 3 ohms resistor, and here it is 13 ohms resistor, and here it is 9 ohms resistor. Right? Now you can see these 13 and 9 ohms are in parallel because these two resistors having two common nodes. Of course, here the common node may or may not connect with any other element. That is not the point here. Okay. So which means here then the equivalent resistance is 13 into 9 by 13 plus 9. Okay. So which is equal to 5.31 ohms. Then now the circuit will become, okay, here 2 ohms and this combination that we can replace with 5.3 and again 3 ohms. So here it is X and here it is Y. So in between X and Y, 3 resistors are there. One is 2 ohms, another one is 5.31 ohms, and another one is the 3 ohms. Okay. Then the total equivalent resistance between X and Y is 2 plus 5.31 plus 3, which is equal to 10.31 ohms. So this is the equivalent resistance R equivalent, okay, RXY, which is equal to 10.31 ohms. So this is how we can find the equivalent resistance between the two terminals by using the star to delta or delta to star transformation. So according to the circuit requirement, so we have to identify whether we should transform the delta to star or star to delta. Right? Okay. Now let us go for the next problem. Okay. So for this particular circuit, again we need to find the equivalent resistance between the terminals A and B. Right? So for that here, let us see is there any series or parallel combinations are there. So these 9 ohms resistor and 3 ohms resistor, of course here it is having only one common node, but the common node is connected to this 3 ohms resistor. So we cannot say these 9 and 3 are in series. Again these 3 and 3 also, of course, having only one common node, but it is connected to 9 ohms resistor. So we cannot say. So again, even these two combination also having one common node, but here 3 ohms is there. And these two also one common node, but the common node is connected to the terminal that we are going to find the equivalent resistance. So that's why we should not disturb this one. Next, in between 3 and 3, again one common node is there, but this common node is connected to 9 ohms. So which means here we cannot simply apply the series and parallel combinations to reduce this network and find the resistance between the A and B terminals. Then what we are going to do? Because in the previous case also, in that case, we have applied the delta to star transformation. But here, what kind of transformation that we are going to apply? Whether it is a delta to star or the star to delta. Okay. So here, as you can see here, this here it is. We can make it this one as a delta. Okay, with the resistors 3, 3 and 9. Okay, 3, 3 and 9. So here, let me draw how we are going to transform this circuit into what is that the star transformation. Okay, so there are two ways to convert, because here as you can see simply these 3 ohms and 9 ohms are in star connection. Okay, or otherwise, in other words, here these 3 ohms and 9 ohms and 3 ohms are in a delta connected. So for this delta connected, we can transform into star connected, right? So which means here one common node is there, okay, and this is the second one, and this is the third one. In between, you will be having 3 resistors. One, okay, let us consider here the common point is S, and in between these two, one resistor, and in between these two, another resistor, right? So now we are going to find the value of, let us consider here it is R1 and here it is R2 and here it is R3. Okay, or in another words, let me draw a simple, for our simple understanding. So here, because we are going to consider these three resistors, so other resistors I am drawing as it is. So these 3 and 3, okay, and as well as here one more 3 is also there, right? Okay, so here this one I am just going to draw like this. So let us draw here 1. This is this 3 ohms. Okay, this 3 ohms, and another one is like let us draw here with this is another, this is 9 ohms. Okay, another this 3 ohms is there. So these 3 ohms, let us consider here, this is the again another 3 ohms. Okay, so here of course here, because at the end of, in between 9 and 3 you will be having the point B. In between 9 and 3 here you will be having the point B. This is point B. Okay, and again this point B is connected to the 9 ohms resistor, the same 9 ohms resistor. Again here I am drawing 9 ohms resistor. So again this is 3, and in between these 3 and 3, okay, again there is a point A, and this is 3 ohms resistor. Okay, fine. So now we are going to convert this one into, because this is one point and this is second point and this is third point. So star, this is 1 and this is 1. Okay, so let us consider this is R1 and this is let us consider R2 and this is R3, and let us consider this is the point S. So now we are going to find R1, R2, R3 values. Okay, so which means we are converting delta into star. Okay, first let us write the equation for the R1, because here the values are different, so that you will get understand clearly. R1, so here this is R1, so R1. So what are the two other resistors which are connected to R1? This particular node, 3 and 9. So 9 into 3 by 9 plus 3 plus 3, the total resistance. And similarly here R2 is equal, here R2 is connected to, in between these two, again 9 and 3. So 9 into 3 by 9 plus 3 plus 3. Similarly R3 equal to, so here R3 is connected to this particular node. So here this particular node, this 3 ohms and 3 ohms. So 3 into 3 by 9 plus 3 plus 3. So these are the equations to find the value of R1, R2 and R3. Right. Then here R1 is equal to, here it is 1.8 ohms. If you simplify this, you will get here also the same. So 1.8 ohms. And here you will get the 0.6 ohms, because it is 3 into 3 by 9 plus 3 plus 3. Right. Then replace these values here and simplify this circuit. Okay, if you simplify this circuit, then you will get the circuit is like this. So see, of course before that here we are drawing the same values, because this 3 point, of course this 3.5 and what is that, this this is 3 ohms, this 3 ohms, 3 ohms, 3 ohms and 9 ohms we didn't disturb. So I am just drawing as it is. So here this is the 3 ohm, and again this is the 3 ohm, and in between these 2 3 ohms resistor, point A is there, right? And again here one more 3 ohms resistor is there. We didn't disturb this 3 ohms also. And again here in between this is one 9 ohm resistor is also there. So we didn't disturb this 9 ohm resistor also, right? Okay, so here there is a terminal S. Okay, so point S, let us consider here it is the point S. This is, let us consider this is 1 and this is 2 and this is 3. Okay, so 1 is connected to 3 ohms, which means here it is the 1, and 2 is connected to this 3 ohms, so here it is the 2, and this 3 is connected to this point B. Okay, so here it is the, let us consider here it is 3. So this is point B again. So first this is S. In between 1 and S, what is the resistance value? R1. So R1, and in between 1 S and 2 is R3, and in between what is that S and 3 is R2, right? So what is the value here? This value is what is that 1.8 ohms, and here it is 0.6 ohms, and here it is 1.8 ohms. So this is the way to transform, okay, this particular circuit to here. Okay, now you can see these 3 ohms and 1.8 ohms are in series, right? And again here, as you can see, these 0.6 and these 3 ohms are again in series. So this can be replaced as 4.8 ohms, and this can be replaced as 3.6 ohms. So now I am just redrawing the circuit by replacing these two combination with the equivalent resistance, and again these two combination with the equivalent resistance. Then now the circuit will become, here this again 3 ohms as it is. Okay, so here the total circuit is replaced with 3.6 ohms. Okay, and here it is 4.8 ohms, and between here the point A is there, and here 3 ohms is there. The 3 and 0.6, here it is 3.6 ohms. So, and then of course here 1.8 as it is there. This is 1.8 ohms, and here the point B is there, right? So in between, one 9 ohm resistor is also there, 9 ohm resistor. Now again let us see, is there any combination or connected in series or parallel? Of course again the same problem here. This 4.8 and 1.8 having one common node, but the common node is connected to 3.6. And here these 3 and 3.6 are having one common node, and the common node is connected to 9 ohms. So again here we cannot simply apply the series or parallel combination. Okay. So again if you see 1, 2, 3, these 3 are in a delta form. So you can convert again this delta into star. So again here let us consider S, and this is 1, and this is 2, and this is 3. So in between 1 and S, one resistor is there, and in between this one resistor is there, and in between this, okay, so let us draw here like this, one resistor is there. Again let us consider here it is R1, R2 and R3, right? Okay, so here R1 is equal to, again R1 is connected to node 2. What are the two resistors connected to node 2? 3.6 and 9. So 3.6 into 9 by 3.6 plus 1.8 plus 9. And similarly R2 is connected to this node 1, and what are the two resistors connected to this node 1? 3.6 and 1.8. So 3.6 into 1.8 by 3.6 plus 1.8 plus 9. And similarly R3 is equal, here R3, what are the, for node 3, what are the two resistors connected to node 3? 1.8 and 9. So 1.8 into 9 by 3.6 plus 1.8 plus 9. Okay, so now we got the values of R1, R2 and R3. Then now just replace this delta with the star and again draw the circuit. So now the circuit will become, here of course here in between these two 4.8 and 3 ohms is there. So here of course 4.8 as it is. Okay, and let us draw here the 3 ohms resistor also. In between the point A is there. Okay, so here this is node 1 as it is, and here node 2, here it is, this is this is 4.8 ohms, and this is 3 ohms. So the other end of the 4.8 is connected to node 1 here, and the other end of 3 is connected to node 2 here. So here it is node 2, let us consider, right? And node 3, okay, so let us consider here it is the S, okay, and here somewhere it is the node 3. Okay, so then in between 1 and S there is one resistor is there, and 2 and S one resistor is there, and here 3 and S also another resistor is there, right? So here in between 1 and S is R2 resistor. Then the R2 here the R2 value is 2.25 ohms if you simplify. So here it is 2.25 ohms, and then similarly in between 2 and S, okay, in between what is the 2 and S, R1 is there. Okay, so in between 2 and S, R1 is there. So here again it is 0. No, sorry, here in between 1 and S, here the values are, this is R1 dash, which is equal to 0.45, and this is what is that, 2.25, and here it is 1.125 ohms. These are the values. If you simplify this, you will get these values. Okay, now here you can see these two are connected in series and these two are connected in series. Okay, and these two combinations are connected in this series. Okay, then finally, just we can see here, right? I mean, again, I'm going to simplify this. So this is again A. Okay, and in between A there is one resistor, and here it is one resistor, and here it is another resistor, and this is the B. So which, because here these two are in series, 4.8 and 0.45, so this is 5.25, and here it is 3 and 2.25, here it is 5.25 ohms, and again here it is what is that, 1.125, so 1.125 is as it is. Then again these 5.25 and 5.25 are in a parallel. Okay, then in between A and B you will be having two resistors. Okay, so one is the parallel combination of this. Okay, so which will become which is 2.625. Okay, and this is 1.125. Okay, then the total resistance RAB, again these two are in series, RAB is equal to 3.75 volts. This is the way to find the equivalent resistance between the two terminals. Okay, so which means here there is no compulsory rule like you should apply only the star to delta or delta to star. Okay, according to our convenience. Okay, according to the network, we should apply the star to delta or delta to star, so that we can reduce the network, so that we can find the equivalent resistance between the terminals A and B. Now the next topic we are moving, which is the mesh analysis. Okay, so here for the DC circuit shown in the figure below, find the current flowing through the 10 ohms resistor using the mesh analysis. So we have to find the current flowing through this 10 ohms resistor. So here the important thing is, first we should identify how many loops are there, and also we should identify the current flowing through the loops, the direction of the loop currents, right? So how many loops are there for this particular circuit? For this particular circuit, there are 3 loops are there, right? So this is loop 1, and this is loop 2, and this is loop 3, right? So in these 3 loops, first loop, what we should identify the current. Okay, so here the loop current or the mesh current in the first loop is depends on the polarities of the source present in that particular loop. So here the polarities are plus and minus, so that we can take the high potential to low potential, the current will flow, so that here we can take the direction of the loop current in the first loop is this way. This is the direction of the current in the loop 1. And when coming to the direction of the current in, of course, here the second loop, it doesn't have any what is that, voltage source. So okay, so that let us go for loop 3, then again we will come for the loop 2. So here loop 3 plus and minus. So again let me draw here like this. Okay, this is the loop current, right? So then in the third loop, okay, so let us consider here the loop current direction is as our wish, because here there is no what is that, voltage source to indicate the loop current. Let us consider here like this. Then here let us consider, here it is the current flowing through the loop 1 is I1, and the current flowing through the loop 2 is I2, and the current flowing through the loop 3 is I3. Now we should write the loop equations. Okay, so for that loop equation we should apply the KVL. According to the KVL, which is the Kirchhoff's voltage law, the algebraic sum of the voltages across any loop is equal to 0. Okay, so which means here, let us say, take here with respect to the first loop that we are writing the equation. Okay, let us start with this what is that, the 4 volts. So 4 is equal to this 5 into I1, the voltage across the 5 ohms is voltage, I mean resistance into current. So 5 into I1 plus 15 into, because in the 15 ohms resistor, the current I1 and as well as I2 both are flowing. But here we are writing the equation with respect to the loop 1, so that we should take the reference current direction is with respect to the loop 1 current direction. So if the loop 2 current direction, which is I2, is flowing in the same direction, then we should write I1 plus I2. And if it is opposite direction, then we should write I1 minus I2. So here, of course, I1, because I2 is opposite to the I1 direction, so I1 minus I2, and which is okay. This is equation number 1. Then coming to the second loop here, for the second loop, okay, let us start with again with this 10 ohms. 10 into I2 plus 8 into, here I2 and I3 both are in the same direction. So I2 plus I3 plus 15 into, again here I2 and I1 are both are in opposite direction, but we are writing with respect to loop 2. So that's why we should write I2 minus I1, which is equal to 0. So this is equation number 2. Then similarly with the third equation, here let us start with 12. 12 into I3 plus 8 into, again here I3 plus I2, because I3 and I2 are in the same direction, okay, which is equal to 6. Let us consider this is equation number 3. Then solve equation number 1, 2 and 3, okay, so that we can find the value of I1, I2 and I3. But according to the given problem, what we need to find? We need to find the current flowing through the 10 ohms resistor. So what is the current flowing through the 10 ohms resistor here? Actually I2. So we need to find I2. Then by solving these 3 equations, we can find I1, I2, I3 values. Okay. So either you can use the Cramer's rule, or by simply you can use the Calc. By using calculator also, we can find these, I1, I2, I3 values by using these 3 equations. Okay. So if you solve, then the value of the I2 here that we will get is 32.34 milliamperes. Okay. So which means the current flowing through I10 ohms, which is equal to 32.34 milliamperes. So this is the way to find the current flowing through this. Not only the current flowing through 10 ohms, if you want to find the current flowing through the 5 ohms resistor, then I1. Okay, if you want to find the current flowing through the 15 ohms resistor, then I1 minus I2. Or if you want to find the current flowing through this 8 ohms resistor, then I1 plus I2. Sorry, I2 plus I3. Like that we can find, okay, the current flowing through any element by using this mesh analysis. Next problem, this is also based on the mesh analysis. So here what they ask us to find the current flowing through this 4 ohms resistor, again by using the mesh analysis. Here remember one thing, to find the current flowing through the 4 ohms resistor, there is no rule like only by using the mesh analysis. Okay, we can use any network reduction technique to find the current flowing through the 4 ohms resistor, but in the given problem they clearly mention we must use the mesh analysis. So that's why we must use the mesh analysis, because without using the mesh analysis also we can find, but here they mention like we must use the mesh analysis. By using the mesh analysis we can find the current flowing through the 4 ohms resistor. Yes, in here also first we should identify how many loops are there. Of course in the given problem they have already given loop 1, loop 2 and loop 3. Okay, then now we should indicate the loop current direction. In the first loop, of course, there is a voltage source, so we can draw the loop current direction is something like this. This is the loop current direction. So this is I1, let us consider. In the second loop, okay, because here the loop 1 current direction is entering towards this one, so we can make it like this. This is I2. And this is the third loop, let us consider, of course, okay. And third loop, yeah, let us consider this is the direction of the current. I3. The same way now we are going to write the equations. Okay, with respect to I1, of course, let us start with from 12. Here 12 into I1 and I2 both are flowing, but I1, I2 both are in opposite direction. So I1 minus I2 and plus here again 3 is there. 3 into, of course, again here I1, I3 both are in opposite direction. So I1 minus I3 plus here 4 into I1, which is equal to 100. Okay, this is equation number 1. Then with respect to loop 2, start with 3. So 3 into I2 plus 50 into, here of course I2 and I3 are flowing in the same direction or in the opposite direction. Okay, so here I2 minus I3 plus 12 into I2 minus I1, which is equal to 0. Let us consider this is equation number 2. Then coming to the third equation with respect to loop 3, let us start with 7 ohms. 7 into I3 plus 3 into I3 minus I1, because I3 and I1 are in opposite direction, plus 50 into I3 minus I2, which is equal to 0. This is equation number 3. So by solve these equation number 1, 2 and 3, then we will get I1, I2 and I3 values. Of course, here according to the problem we need to find the current flowing through this 4 ohms resistor. So here we need to find only the value of I1. Okay, so if you solve these 3 equations, then you will get the value of I1, which is equal to 10.163 amperes. So this is the current flowing through the 4 ohms resistor, which is equal to 10.163 amperes. So here the important point is to write these equations. So to write these equations, first we should indicate the directions of the currents in the loop. Okay, so that we can write these equations. And you can use any one of the technique to solve these equations. Okay, then you can find I1, I2, I3 values, so that we can find the current flowing through any resistor by using this mesh analysis. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.